Good morning. Here we are headed out again in chapter 23. I hope that first lecture for chapter 23, I hope that was useful. I know we went over a lot of stuff. We did a fair amount of review of gravitation, and we're actually starting off with another gravitation example here. But remember, in all of these examples that we look at, when we're looking at fields, forces, potential energy, those for us are going to become the big four. Those are the big four quantities for both gravitation and for electric forces that we want to be able to keep track of. And once we realize, okay, it's the big four, how do I, given some information about one of those, how do I calculate all the other quantities? That's what we want to really emphasize here. And we're going to look at a lot of examples. We've got a couple more lectures on chapter 23. So we took a lot of time on chapter 21 with the idea of really getting the foundation in place. And now in chapter 23, we're kind of back doing the same thing. We want to make sure we're really clear how these different quantities are related. So at the end of last class, what we had started looking at was planet Earth, for example. It doesn't have to be planet Earth, but here's a planet, or here's a star, here's an object. Maybe it should be a planet, because we're going to lift the object off of the planet surface and then slowly propel it into space. We set it at a constant velocity in order to think about how the formula should be put together. Now, how would this problem look if it were an electric problem? If it were an electric force problem instead of a gravitational force problem? And what it would look like is that would be a bunch of charge. So instead of planet Earth, there would be, well, a spherical charge, since we're studying now spherical symmetry of spherically symmetric objects. If we had a sphere that had a spherically symmetric distribution of charge, then there would be another charge here, and we could ask how much force would be acting on that charge, and what would it take to lift the charge away or to allow the charge to return. Now, the complication we said with electric forces, one of the interesting features of electric forces, is that they can be attractive or repulsive. So if we're thinking of a strict analogy here, where we get a potential energy expression with the minus sign out front, for example, that would be, say, a positive sphere with a negative charge out here. Opposite signs are going to attract. Now, the default case for electric forces is that everything's positive. So we start off solving everything as if there are only positive charges in nature, and then we go back and ask ourselves, okay, how would this change if there were negative charges, if some of these get flipped over into negative charges? So everything we calculated here would be identical if we were looking at charged objects. So this could be big Q, that could be little q. The distances could stay the same. The force for the electric force between charges would be little k, q. So everywhere there's a big G as a force constant, we just take that out and put in little k as a force constant. And remember now, little k, 8.99 10 to the 9th newtons meters squared per coulomb squared. So once we get down to our final formula, this would be little k, big Q, little q over r. The minus sign would not be there, because if I go back to the idea of the only charge in nature is all positive, it's no longer an attractive force. That would be a repulsive force, and that would give us a plus sign. Okay, so again, looking ahead, that's what we would expect. Now, I did a little bit more here. So let's look at gravitational potential energy. This is the same diagram as before. What I did was I picked a couple locations, one on the surface of the Earth and one out in space. Now, the out in space I picked as 25,000 kilometers. The radius, where is it? Should have written it down. The radius of the Earth is 6.37 thousand kilometers. So here is the distance at point A that I'm starting at, and then here is the distance at point B where we would like to launch a satellite. So satellites for the GPS system. There's a whole bunch of satellites that maintain the GPS system for us, and they're in orbits about 25,000 kilometers from the center of the Earth, not from the surface, from the center. All of these formulas, think back to Physics 4A, gravitational chapters, chapter 6, chapter 7 and 8, where we looked at gravity and then we looked at potential energies and such. All those distances, all the R's were measured from the center. Okay, so I plugged the numbers in. Now, I went ahead and treated this as just a mass of 1 kilogram. And what it said was, something sitting here on the surface of the Earth has a potential energy of negative 63 million joules due to its gravitational interaction with the Earth. So that's an energy debt. That's a negative value. In order to get that object that is currently sitting at the surface of the Earth, if I wanted to get that out into space so it never comes back again, I would have to come up with 63 million joules of work. So we do that when we launch satellites, when we launch spacecraft. We just had the rover, a new spacecraft, land on the surface of Mars. Perseverance, right, I want to say. Perseverance has just landed. Absolutely amazing. It was great to watch this. It was live streamed through YouTube. I got to sit there, maybe some of you did too, as if you're right at Mission Control at Caltech, at the Jet Propulsion Laboratory at Caltech, and watch the first photos come through. And now they got photos showing, as the rocket slowed down, releasing and lowering the spacecraft onto the surface. Just amazing photos. So anyway, in order to get a spacecraft away from the Earth, far, 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 we've got to come up with 63 million joules of energy, and that's for every kilogram of spacecraft. Now, if we want to put a satellite into orbit at 25,000 kilometers, I calculated the potential energy there. Oh, a satellite at 25,000 kilometers from the center of the Earth still is in an energy debt in terms of its potential energy. So I really wouldn't need this 63 million joules. I just have to have enough to go from being in debt 63 million joules to being in debt 16 million joules. That sounds like 47 million joules. So I just need 47 million joules of work in my rocket available for every kilogram of spacecraft that I want to launch out to point B. Now, again, heading out to infinity would be 0 million joules. At that level, the potential energy is defined to be 0 out there, and to get out to infinity, I would need to come up with that full 63 million joules. Now, how does that change for gravitational potential? And for gravitational potential, all we got to do is drop little m from all of our formulas. Everything we did for gravitational potential energy can be switched over into gravitational potential, V, simply by dropping that mass. Now, what I did do, if you noticed, the mass I used here was 1 kilogram. So I can take the potential energy required for per kilogram and immediately just copy those numbers over, right? If that's part A and part B of the exam, on part B I say, see the first part, just divide through by the mass. Take the potential energies, divide through by the mass, and that'll tell me how many million joules I need per kilogram. How many million joules I need per kilogram to get out to point B. Okay, so that's how potential energy and potential work, it works exactly the same way for the electric force. Let's, not one more slide. So getting used to this negative stuff, the way this works in terms of graphing is that I have plotted the potential energy function, which is 1 over r. And what it says is the potential energy at B is higher than the potential energy at A. They're both negative quantities, but potential at B is higher, and I need enough work in my rocket ship to lift it out to this less negative potential energy. And again, the two graphs are just side by side. They just look exactly like each other because the difference between the two graphs is just determined by putting in the mass of the spacecraft that we've launched. Okay, now we're ready to do the very same thing with a spherically symmetric distribution of charge. Now, we're going to start off assuming that all the charge is on the surface. Now, the way the textbook tells you that is they say we have a conducting sphere. And if we remember back to chapter 22, maybe chapter 21 also, we learned that if I put charge on a conductor, a metal sphere, the charge is all going to migrate to the surface. So that leaves no charge within the sphere, all the charge concentrated just along the surface. But because it's spherical, it's a spherically symmetric distribution of charge. And that says that the E field outside will be spherically symmetric. It'll follow our formula, kq over r squared. So they're saying determine now the electric potential given that we know what the electric field is. How do we determine what the electric potential would be at a certain location? Okay, so let's try this. What we're going to do here is we're going to draw the same picture we drew before. So now the big sphere is charge big Q, and big R is still big R, and little r is still measured from the center out to some location. How did I get point A there? Oh, okay, this is point C. Sorry, I changed the letters. A now is right at the center. B is at the surface, and C is way out here. And so I'm going to let variable little r keep track of all possible distances. So let's think about this. Little r could, if I'm looking at a point between A and B, which is inside the sphere, there's no electric field there. And that's because it's a conductor. So we learned about that in chapters 21 and 22. If there's a conductor, the charges will keep moving until the E field goes away. And then we showed that for a force that behaves like 1 over r squared, something like the electric force, that means that all the charge will go to the surface. Charges don't, because it's a 1 over r squared force, the charges don't distribute themselves within the center. Any excess charge shows up at the surface, and there's no excess charge within the rest of the sphere. So the E field inside is going to be 0. And then outside, we had solved this using Gauss's law. Now, I've written this in vector notation. I've kind of gone back and forth. From time to time, I want to write it in full vector notation. The little unit vector here, unit vectors are going to be represented as little e's with a little hat on top, and then a subscript which tells which direction. So the unit vector E sub r is a unit vector that identifies the direction pointing away from the center of this object. So these little drs are actually in the direction of the unit vector ER. So this is what's outside. Now, what we're supposed to be able to do from those slides that we looked at earlier is we're supposed to be able to calculate potential differences by integrating along the path of the electric field. So let's try that. What we can do is let's do this first. Since we have electric fields directed from point B out towards point C, what we know is that the potential at point B is going to be greater than C. So again, this is kind of our list of things that we can immediately write down. just by our conceptual understanding of how electric fields and electric potentials work. So if the electric field is directed outwards, that means it's directed towards lower and lower electric potential. As I get farther and farther away, the electric potential is going to drop off. So VB is going to be greater than VC. Now, another thing I want to point out here is, how does the electric potential at A compared with the electric potential at B? And there's always this tendency to say, hey, if the electric field is 0 inside, the electric potential must be the same thing, and that's just not true. So the electric field inside is 0, but the electric field at the surface is not 0. So I've got an electric field all the way up to point B, and I know that I can use this formula to represent the electric field at point B. What an electric field of 0 inside tells me is that there's no difference in the electric potential moving around within the volume of the sphere. If I've got a region of everywhere inside the sphere where there's no electric field, everywhere within the sphere will be at the same electric potential. Now, when we carry out this integration to find out what the electric potential is at point B compared with point C, boy, I hope we got this right. Yeah, so we carried out this integration. This term of the integration becomes our potential at point C, and this becomes the potential at point B. Now, I can't integrate directly from A to C, and that's because the electric field formula changes. The function that tells us how the electric field behaves is different inside than it is outside. So I can't integrate from A to C. I have to break the integration into 2 steps. And you guys have seen this in your calculus class, right? If I've got a function that has a different form to it in 2 different regions, I can't integrate across that boundary. I have to integrate on one side of the boundary and then integrate on the other side of the boundary and then add the 2 effects together. So that's what we're going to do here. We're going to integrate from the surface, point B, out to an arbitrary point out in space. And what this tells us is that that difference in potential will be given by this expression. If we allow little r to go all the way out to infinity, well, little r is going to become zero. If little r becomes infinite, the potential becomes 0. So at r equals infinity, the electric potential becomes 0. Now I got a minus sign on here because what this integration is telling us is how much the electric potential drops off. As I'm headed outwards, how much is the electric potential going to drop off? So what I can do then is take the absolute value of this, kq over r. If kq over little r represents the potential way out at some distance, then kq over big R represents the potential along the surface. So that tells us that outside the potential is kq over R. Sorry. At the surface, let's do the surface first. At the surface, kq over R is going to tell me what the potential has accumulated to. And then since there's no E field inside, that kq over R stays fixed. So you can always think of it this way. In the gravitational case, we had to think of propelling the spacecraft away, trying to get it back to 0 potential. When I have a positive charge here, and I start with a positive charge out at infinity, they're repelling each other. And so it's now going to require work, it's going to require a force over a distance to push that positive charge towards this big sphere of positive charge. So I start with a positive charge out at point C, and I push on it, and I push on it some more, and I push on it some more. And what happens is, I'm going to build up more and more potential energy, and I'm going to build up more and more potential. So anytime I am traveling opposite the electric field, I am headed into regions that are at higher and higher and higher electric potential. So I started off at 0. I climbed all the way through that electric field. I climbed it up against that electric field to get to point B. But once I got to point B, I found out the electric field is gone. So the electric field inside is at point B. So it's kind of like a plateau. You can think of this as climbing electric potential. And so I had to climb against that electric field. But once I got to the edge, then I hit a plateau. And the electric potential stayed fixed through that inner region. Now, you might ask yourself what would happen if instead of all the charge around the surface, what if the charge were uniformly distributed throughout the sphere? What would that change? Now, let's do that. Let's take a look at that example. Here is the very same example. Wasn't included in the text, but I added this in. So example 23.4, the extended version. And now we're going to look at a charge sphere that's uniformly, where the charge is uniformly distributed. So if the charge is uniformly distributed, it says it must not be a conductor. It must be made out of insulating material. Because with an insulating material, when we manufacture it, we can manufacture it in a way where we put extra charge, or we remove some of the electrons as we manufacture that, and that will put a permanent charge throughout that sphere. And so anyway, here we go. Here is a sphere, and it's got a uniform charge distribution inside. So this time, the electric field inside it's not 0. In fact, back in the previous chapter, we solved for this in using Gauss's law, and showed that for a sphere of charge, where the charge is uniformly distributed, the E field outside looks just like it did before, kq over r squared, and the unit vector is saying we're directed away from the center. Right when we get to the surface, what this formula tells us is that it will be kq over big R squared, again with the unit vector. And then finally, when we moved inside, Gauss's law showed us, or we did this calculation, we showed that the electric field drops off linearly until we get to the center. When we get right to the center, the E field will be 0. Now, the E field is 0 at the center because right at the center, being surrounded symmetrically by this distribution of charge, all the E field effects cancel out. So it's because of cancellation that the electric field goes to 0. Not that those charges are not having any effect anymore. It's just that when we combine all their effects together, they cancel out. They give us a net E field of 0 at the center. So again, I've got, well, 2 different formulas. I've got one formula telling me what function tells us about the electric field outside. I got another formula telling me how the electric field will behave inside. The surface, I can get that from either one of these. It turns out the value at the surface is continuous with the inside formula and the outside formula. All right, here we go. Now, since the outside formula has not changed, right? If we go back and ask what happened when we had a conducting sphere, the formula outside here matches the formula here. If we're outside the charge distribution, doesn't matter how the charges are distributed as long as they're spherically symmetric. So this is not changed, and that says that if we go out to infinity, which is located outside the sphere, and calculate the electric potential in the region outside, we're going to get the same formula. The electric field region outside here was not affected. by bringing all the charge and moving it around inside the sphere. And so the electric potential formula will be the same. At the surface, the electric potential formula is the same. Okay, what happens when we get inside? Things change. So before, inside was 0, and so delta V was equal to 0, delta V, and that meant that the V was uniform inside. But now we're going to have to carry out an additional integration. We're going to have to carry out an integration within the sphere to find out what the potentials are like. So here's what that looks like. Let's move inside the sphere. I'm calling this point right at the center, point D. I'm calling it an arbitrarily picked point between the center and the surface C, and I'm using little r to represent that. So the little r's get used for outside the sphere. That's one set of calculations. And then the little r's get used again for inside the sphere. It's a different set of calculations, but we use little r for both. We did this in chapter 22 with Gauss's law, so kind of that same approach. Now, the electric field will be directed outwards away from the center, away from point D, through all of this. So I went through and I integrated the electric field along that path. There's the expression for the electric field. And what I came up with was this. I came up with going from point C to point A clearly reduces the electric potential. That's because we're following the electric field line. So the potential at C is going to be higher than the potential at A. And the potential at D will be the highest value of all of those locations. Again, if I use the climbing analogy, right? I start out here at infinity, I climb up against that electric field, I climb all the way to the surface, and then I continue to climb because the electric field is still opposing my path. My quest is to reach the center of that sphere. In order to do that, I have to continue going up against this electric field. Now the electric field is getting weaker. Once I cross point A and head inside, the electric field is beginning to drop off. But it's not 0, so I still will have an increasing electric potential as we head towards the center. So I took this delta V that I calculated here, which was negative, and what I said was the potential at point C can be determined by taking the potential at the surface and then adding on the magnitude of delta V. So at the surface, we determined that the electric potential at that point was kq over big R. And now I have to add this amount on, the kq over R. I factored out some big R's here, I moved some things around, and ended up with this expression. And then what I was able to do was combine the kq over R at the surface with a kq over R times 1/2. This is what I got. VC kq over R, 3/2 minus 1/2, little r squared over R. Now that's for inside only. That's my inside formula. So for anywhere between 0, right at the center, and big R, anytime little r is less than R, that's my formula for the electric potential inside. So let's ask a couple of very, very, very important questions. What does that say the voltage is, or the electric potential is, at the surface? Well, at the surface, little r is equal to big R, and if I plug in big R, the r's cancel, and I get 3/2 minus 1/2. That gives me 1. That gives me kq over R, and the good news is that matches the answer we had before. So that's good news. We expect the voltages have to match up at the surface. Now, what happens right at the center? Well, at the center, little r is going to be equal to 0. If I plug that into my formula for inside the sphere, a 0 here leaves me with this factor of 3/2. So it says, okay, at the center, the potential will have reached a value of 3/2 kq over R. At the surface, the value is kq over R. At the center, it's going to be larger by a factor of 3/2. 50% larger. because of that additional climb through the electric field. Let's look at some graphs for that. So here is this sphere. Remember, it's uniformly charged now. The electric field formulas, which we solved back in the previous chapter, chapter 22, the electric field was kq over r squared here. I should have written the formulas in. I had plenty of room here. This was kq over r squared. This was kq over big R squared, r over big R. This was a linear increase, and then a 1 over r squared drop-off once we crossed the surface. What that led to in terms of electric potential was 1 over r behavior outside, leading up to a kq over r at the surface. And then there is a quadratic. That's a polynomial. If you go back and look at the formulas here. Again, I could have put the formulas on this page, but we can flip back and forth. This is the formula we came up with for the electric potential inside the sphere. That's a polynomial, and it's a polynomial that's a square in R. So what that says is, this is a quadratic or a second order polynomial flipped upside down. That's what that is. And it curves as you get closer and closer, and as the electric field is dropping off, there's less and less of an effect, and eventually it just levels off right at the center where there's no electric field anymore. It levels off to a value of 3/2 kq over r. Okay, so that's it. That's how it works. That would be the potential measured at every possible location, inside, outside, at the surface of a uniformly charged sphere. All right, let's move on. So we've seen this. This is just kind of a review here. So here we are at the surface. Here we are 2 radiuses away, 3 radiuses away. The electric field is dropping off like 1 over r squared. Now, which case is this? Is this where the charge was all on the surface? Or is this the case where the charge was uniformly spread through the sphere, and this sudden drop-off down to no E field at all inside tells us, oh, that was the charge all along the surface. Doesn't matter if it's a conductor or an insulator. If all the charge is on the surface, then the electric field inside would be 0. So that's what it looks like. And here was the potential. The potential was 1 over r up to the surface, and then it stayed fixed at kq over r as we headed inside. What changed when we rearranged the charge so it was uniform throughout the sphere, and instead of a sudden drop-off, the E field dropped off linearly until we got to 0 at the center, and that got replaced with a sloping linear electric field line. And then the electric potential continued to go up, curved up, and we can look at the previous slide, it's all there, right? There's the 2 different graphs. All right, here's a topic that the textbook threw in. They put in like a lot of words here, but what they're really, let's see if we can simplify this. It says that there's a breakdown voltage on any device, and a breakdown voltage says this. It says that if I take an object, we picked a sphere in their example. This is actually an example that's on that previous slide, but I would have to read for 15 minutes to find out what it's about. So anyway, here is a sphere. I'm going to put charge on here. As I put more and more charge on, the voltage goes up. These are the formulas we just derived. So the the voltage continues to go up, and the electric field at the surface continues to go up. So they're both proportional to charge. Here is some kind of a conductor, or it doesn't have to be any conductor or insulator. It's acquiring a bunch of charge. Materials that are just placed in air, there's what's considered to be a limit to how large an electric field can be in different materials. And they might have, maybe they don't have it here. I thought they had a table of different materials. In any case, what happens is if the electric field within air exceeds 3 million volts per meter, the air begins to conduct. So that's a large enough electric field that the electrons on the nitrogen molecules and the oxygen molecules and such, electrons can separate and then start to conduct through the air. You know, something like an electric spark or lightning. So if we get to 3 million volts per meter, now that's quite a large electric field that we can place onto an object. Now this is referred to as a breakdown voltage, but it's really a breakdown electric field. Now breakdown voltage says for this device, to what voltage can we charge it until we start to see it spark. It starts to be sparky, it's generating some little bolts of lightning as a result. Now what we can do is we can take this limit for the electric field for air. They gave us a certain radius. These are the formulas. Now if I take these two formulas and kind of merge them together, what it says is at the surface the breakdown voltage will depend on the limit to the electric field. What's the maximum electric field we can manage? And for a spherical geometry, these formulas are for spherical geometries, it just becomes E times R. If it were a different shape, it would be a different breakdown voltage. So it says that for a spherical conductor, the breakdown voltage is going to be, I plug the numbers in, it's going to be 30,000 volts. Okay. If we continue to use a sphere, but we pick a different radius, if I go to a larger radius sphere, it can hold a higher voltage. So it tells me that if I build some kind of electric device, you know, something with the grid, the power grid or whatever, and that object is going to get charged, how big do I have to build it to make sure that it doesn't shoot off little sparks of lightning? And so I've got to go to a large enough R so that my breakdown voltage would be above whatever the operating voltages are going to be. If I've got a transformer or something and it's going to be operating at 10,000 volts and you know, if I got an object that needs to be able to hold that much voltage and not spark, this would be an example of determining what dimensions, how large would that object need to be. This is just a reminder of the same formula, so this is just the Book's diagram. It's worth going in and noticing that for the most part they switched over. They're using 1 over 4 pi epsilon naught. I am continuing to use little k. I mean, they first introduced it. I think it was the right thing to do. They've switched back over to kind of this more historical approach. I do see more and more in textbooks that more and more effort to switch over and use little k instead of the 1 over 4 pi epsilon naught. I'm going to say for you guys, you need to know both. You're going to run into both in your educational careers, is my guess. And then here is the electric potential due to different point charges. So we had come up with this formula. We had derived this for any spherical distribution of charge. Point charges do fall into that category. And that says that if I have a positive point charge, I am going to have a potential formula that's K, see that's K, 1 over 4 pi epsilon naught, Q over R, and it's going to be positive everywhere. So if I have a positive distribution of charges, such as a point charge, the potential everywhere surrounding it is positive. If I have a negative charge, every point around that is going to have a negative value of potential. Now this positive and negative, again, it doesn't mean one is more dangerous or less dangerous, or it's just arbitrarily the way we keep track of electric potential. And in terms of what's safe and what's dangerous, again, it's the delta V that we want to look at. We always want to be looking at a delta V between two locations in space when we're asking those questions about safety. All right, this says I want to take two positive charges and I want to bring them close to each other. And here's what the problem looks like. So, again, I'm going back to gravity. So if I had two masses, they would have a certain force acting on them. There's a potential energy. It's an attractive force. The potential energy would be 0 at infinite separation. And as I bring them close together, the potential energy drops. Now in this case, we're going to take two positive charges, which are repelling each other. Now for a repulsive force, again, at r equals infinity, we're going to define that as 0 potential energy. But notice this time, the potential energies are always going to be positive. If I take two positive charges, I got to do work. I got to push them together. I got to push them with forces and to hold them. If I get them close to each other, they're storing energy. If I let go, they shoot back away from each other again. So in the problem, they gave us the values of the two charges. They're both positive. Now they could have both been negative, and the problem would work out the same way. If one had been negative and one positive, then no longer would we have a repulsive force. We would have an attractive force, and the potential energies would be negative. Now, how am I going to keep track of all those signs? Well, the formula itself does not have a negative sign on it. And if both Q's are positive, if both Q's are negative, the overall potential is positive. The potential energy is positive. If we have one of these Q's is positive and one is negative, then this becomes negative. So again, when we were looking at the vector quantities, electric force, electric field, we usually didn't pay attention to the charges once we had the diagrams drawn. So we did, let me say it this way, we did pay close attention to the charges, and we drew a diagram, and we labeled all the directions based on the plus and minus signs on the charges. And then when we put the numbers in, we ignored the charges. But when we're doing these scalar calculations, electric potentials, electric potential energies, instead what we do is we let the minus and plus signs go into the formulas, and they'll keep track of whether or not the potential and potential energies are positive or negative for a given situation. So let's see what came of all this. Here's the formula. I plugged everything in. Remember, potentials and potential energies are 1 over r for point charges, not 1 over r squared. And so I put that value in. I ended up with 1.08 joules when I've brought them 50 centimeters from each other, 50 centimeters. And then by the time they get to 1 centimeter now, they are 50 times more potential energy. See how the potential energy behaves like 1 over r? If I bring them 50 times closer, there's 50 times as much energy being stored. Now, the charges here are in microcoulombs, and that's because a coulomb is a lot of charge. So everyday kind of charged objects are going to be in microcoulombs. Little k, 0.99 10 to the 9th. I guess that covers all the units and such. We'll come back. I think there's another example later in the chapter where we start looking at potential energies with point charges. We'll come back and look at some of these. These are important problems, and unfortunately they're kind of scattered through the chapter. They're not as concentrated as they might be. Now, here's an interesting question. Here's charge 1, charge 2. They're both 50 microcoulombs. This one's negative and this one's positive. Now, I don't really know if you remember if this is familiar, but back in chapter 21, we did this problem, but we were calculating electric fields. Now, electric fields are vectors, and that meant that we had to calculate x and y components, and that was a lot to calculate. For vector quantities, the calculating x and y and sometimes z components, and then combining all the components together and carrying out vector addition, that was a fair amount of work that we had to do. One of the features of electric potential and potential energy is they're scalars. They are scalar quantities, which means if I just add the numbers up, I'm done. I just have to find out the contribution for each one. So at point A, none of this directional information matters. All I have to know is when I'm at point A, I am 30 centimeters away from a positive 50 microcoulomb charge. I am 60 centimeters away from a negative 50 microcoulomb charge. That's it. It doesn't matter where Q1 and Q2 are. I don't have to keep track of directions. I just have to know distance and how much charge is it. Let's see what this looks like. So at point A, I said, look, the overall potential will be a contribution from charge 1 and a contribution from charge 2. I factored out the common value of K, and then I just put charge over distance, charge over distance. It turns out that I was closer to the, is that right? Closer to the positive charge. I've got to go back and check here. I am closer to charge 2, the positive charge. So, yeah, I did get everything labeled correctly. Huh, imagine that. So I was twice as close to the positive charge. As a result, I'm getting a positive contribution that is twice as large as my negative contribution. It just depended on distances and the amounts of charge. So when I moved to point B, now point B is kind of an interesting case because, look, point B is equal distance. They didn't draw this in, but this is also 40 centimeters. See that isosceles triangle right there? So that's 40 centimeters, that's 40 centimeters. I don't need to carry out a calculation because I got two charges, same magnitudes, opposite signs. Same distance from point B, their effects will exactly cancel in terms of electric potential. Now, if this was an electric field calculation, I would have to identify the directions, I would have to break into X and Y components, I would have to show that these components cancel, these. It would be a pretty detailed problem. But here, when I carry out the addition, it's just scalars, there's no components. I just add those two numbers together. Because the two numbers are equal in magnitude, opposite in direction, they cancel out. If I am equal distance from a positive charge and a negative charge, where the two charges have the same magnitude, the voltages are going to cancel out. The E fields will not. I have to do vector addition for the E fields. They will only cancel under exact opposite directions, but is that true? No, that's not even true. They won't cancel. But the potentials will. So there are certainly times when the potentials cancel out pretty readily. Now, it says here that the potential due to an arbitrary sum of integration. So, oh no, I knew this was going to happen. I was a little worried about this. Okay, what's happening here is we're going to start doing some integrations. Okay, I know, sorry about that. And so what we're going to do is we're going to start with that ring of charge. Now, you guys remember the ring of charge. We did these back in chapter 21 with the electric field. And the integrations typically are going to be much easier because voltage is a scalar. Now in this case, here we are along the axis, a distance x, there's a little bit of potential being generated from that little bit of charge, but notice the entire ring of charge is all the very same distance from point P. So when we set this up, now you guys know point P always turns into point A in my diagrams. What's going to happen here is a little bit of charge is going to generate a little bit of potential. I've taken my formula for a point charge and turned it into an infinitesimal formula, and then I'm just going to integrate over that charge distribution. Now, R is a constant, so it turns out that if I just leave this as little r, the voltage here is kq over little r. But the little r here is this hypotenuse distance. So I could write it this way, but I have to remind myself, if I want to write this as a function of x, it's r squared plus x squared to the half. Okay. What about if we now fill in the disk? We also did this problem back in chapter 21. So this looks similar to the electric field calculation, but again, the feature here is I don't have to keep track of directions. There are no sines and cosine factors for components. And so each ring on that charged disk is giving me this contribution. That's what we solved. If we go back to here, that's what we had solved for, was that the potential at point A due to a ring of charge, kq over little r, where r is equal to r squared plus x squared. Now in this case, it's not quite as easy. So I'm going to move some variables around. I'm going to call this distance x. Big R now is the radius of the entire disk. I have to integrate over little r. So I'm moving little r to here to use this as a variable of integration. So I've redefined a couple of quantities, sorry about that. The distance from the charge out to point A is x squared plus r squared. That went into my denominator here. Now, this also is an integration I looked up in the chapter, in Appendix A in the back of the book. So this is not a common integration that I'm using all the time, so I looked it up. And, oh, I take it back. No, this one I actually did solve. So in this case, I did a variable substitution. Now, I guess I should come over here first. Little r is my variable of integration. The disk area here is pi r squared. The ring area, the area of each ring, is 2 pi r, that's the circumference around, with a thickness of dr. Now we've seen this before, and that's why I'm moving through this a little quickly. We saw this back in chapter 21 when we integrated for the electric field. So the dq formula that I came up with looks the very same as it did back when I was integrating an electric field. So that gets substituted in for dq. I did a variable substitution with u and then du and was able to get the integration set up as du over u to the half. I changed the limits based on these formulas for u, and then I carried out the integration, and that's what I got, and it looks awful. I wish it would have been a simpler formula, but it's not. Anyway, this is the electric potential measured along the axis of a circular disk of charge. Now let's push this a little further. So here is my disk of charge, here is point A, here is distance x. This is what we calculated on the previous page. That is a function. I could plot that out. I could go to my graphing site that I online and have that site plot this for me. So I could plot that function. What do I find out is this. I want to find out two things. What happens when x goes to 0? What happens when I go right up against the surface of that disk? And it tells me that the potential right at the disk is 2kq over r, over big R. So depending on how much charge is there and what size the disk is, that's the potential right up against the disk. Okay, good to know. That has allowed me to go in and calculate the potential. What happens to the potential if I get far, far away? Now, back when we were doing electric fields, we like to point out that if I get far enough away from any point, any charge distribution, that charge distribution is going to look like a point charge. At far enough distances, everything looks like a point charge. Is there a way I could take this expression and show that in the limit, when x is much, much bigger than r, this reduces to a point charge? So I took this expression, x squared plus r squared to the half. I'm using that approximation technique that we've looked at back in chapter 21, and I'm applying it once again. I factored out the x to get it into a 1 plus format. And then if you go back and use that same approximation, 1 plus r squared over x squared to the half, where x is much bigger than r, approximates out to this. Now, remember when we did these approximations, the terms are getting much, much smaller very, very fast. So, and this is what you guys learn in your calculus classes, right? So, what I've done then is I can replace this expression with this 1/2 in it with, this expression here with an x times the approximation that we came up with, when I do that, this entire expression reduces. The x's cancel out. So I have an x cancel, and I'm left with 1/2 r squared over x. When I substitute that in for that expression in the brackets, becomes kq over x. So again, we had to use approximation techniques, but we have been able to show that the electric potential surrounding this charge distribution is equivalent to a point charge once x is much, much larger than r. All right, now we did a couple of examples. We went in and we solved for the potential along the axis of a ring of charge. We solved for the potential along the axis of a disk of charge. And now what we can do is this. We can use our formula of V is equal to minus the electric field. What we can do is use the reverse of that. And the reverse of this formula is that I can take partial derivatives of the potential, and I can take partial derivatives in the x direction, in the y direction, in the z direction. Taking those partial derivatives will give me the components of the electric field at that location. So what's happened here is this. The electric field is a vector. Vectors have 3 components. Now, how do I get from a vector like the electric field to the potential, which is a scalar? And it says that, the potential only needs information about the electric field along a particular path. That's how we got rid of the vector and replaced it with a scalar. Now we've got to try and go back the other way. The inverse of carrying out this integration with the dot product is to carry out a series of partial derivatives in the x and the y and the z directions. And taking this expression and taking these partial derivatives with a minus sign, same as the minus signs we had before, will give us the electric field components at that location. So let's try this with a ring. With the ring we had gotten this formula, the kq over x squared plus r squared to the half, which we could write this way. We need to take a derivative. Now, we know that the electric field is going to be exclusively in the x direction. If I am looking at a locations just along the axis, I really only have to do that one partial derivative. And you guys know how partial derivatives work, right? Partial derivatives are the best because they look cool. You know, they have that Greek delta, little delta letter instead of d. Your friends are going, wow, what kind of math are you doing? And you say, I'm doing partial derivatives. So the partial derivatives are really cool, but they're actually easier because when I look at this formula, if I'm doing a partial derivative, with respect to x, I only have to consider x dependence. Now in this formula, that's all we have is x dependence, but in other formulas, we can just look at the x or the y or the z dependence. I don't have to keep track of all 3. Anyway, carrying out the integration, or the derivative, the partial derivatives of this expression to get the x, this should say ex, it's the e field in the x direction. I just followed the rules for differentiation and it worked. Now what I mean by it worked is go back and compare this with chapter 21 when we did this example, and we got that formula. So we've done it both ways now. I think we can go back and forth. If somebody gives me an expression for the electric field in a region of space, I have to know it more than just one point. I have to know what the functional form is, because what I need to be able to do is integrate over that electric field to get the potential. So I have to be able to integrate over a region to get the electric potential. Now, if I start with the potential, I can get back to the E field by taking these partial derivatives, so we can go back and forth between electric fields and potentials. In some situations, it's easier to solve for the potential and then use the derivatives to calculate the electric field. In other examples, it's easier to solve for the electric field first and then integrate to get the potential. Sometimes it's just easier to do a direct integration of both. So for better or worse, this gives us more than one way to go in and calculate an electric field or a potential. I've got direct integration techniques, which will always work. For electric fields, we have Gauss's law. And now, if I know the potential, the functional form of the potential, I can calculate an electric field set of components. And if I know the electric field, I can calculate the voltage. Here is the other example. So the other example is, and somehow the diagram on this one got left out, but it's this one. Oh, there it is, right there. So on example 2011, we first of all calculated the electric field at point P. Now we're going to calculate the electric field at point P for a disk. And it's the very same idea. What we're going to do is start with a disk of charge, write down the formula that we had just derived, and then take partial derivatives. Now again, this is only dependent on x. We're only looking at the axis, but taking the derivative gives us the formula that we arrived at back in chapter 21. All right, so it seems like it's working, right? Let's do this. Let's take a look at what we call equipotential surfaces. We looked at an example kind of like this before. This is maybe a better diagram that the book has provided for us. Let's say that we've got some plates set up, and here are the E fields. This is going to look kind of like our lab on electric potential and electric field. So between the plates, we have these electric field lines. Now we said if we stay away from the edges, the electric field lines are pretty uniform. But once we get near the edges, it's not quite so uniform. In any case, what we can draw inside that region is a series of equal potentials that the electric field crosses. Now, by definition, we have set the negative plate to be 0 volts. That's arbitrary. We didn't have to do that, but that is a common place to set the 0 potential. And then we got a power supply of 20 volts and charged up these plates to a difference of 20 volts. And that says that since I have a uniform electric field, kind of in uniform gradations, I'm going to drop from 20 volts to 15 to 10 to 5 to 0. Now the electric field lines are showing paths of certain electric field values. So the electric fields are going to be directed across what are called equipotential surfaces. So those green dashes, those are surfaces, right? There's a plate which has an area to it, and all of those surfaces have areas to them also. And that's a useful way just to stop and think about how the electric field and the potentials are related. Now I think we're coming up on probably a good place to wrap this up for the day. Maybe we'll get started with this. And so here is a point charge, and what they've done is they've drawn equipotential surfaces. Now if it's a point charge, the point charge will be surrounded by equipotential surfaces that are spherical. So here is a sphere that corresponds to the 30 volt equipotential surface. And then here is a sphere that corresponds to a 20 volt equipotential surface, and here's the 10 volt. Now they're not evenly spaced, and that's because the formula for this, oh, they already did the problem for us. Well, we're going to go through and show what the distances are. So let's take a look at this. We have a charge that's, it's only 4 nanocoulombs. It's not much charge. So here are those equipotential surfaces, and we want to know what the R value will be, where R is measured from the center of the charge out to each of those equipotential surfaces. Now the charge is at 4 nanocoulombs, that's 10 to the minus 9 coulombs. Oh, and then the minus 10 to the minus 9 cancels the 10 to the 9 in the force constant, and we are left with, now I'm solving for radius here, so or distance, sorry, it's spherical, so radius is distance, but I really should be calling this distance. So the distance from the center for the 10 volt equipotential surface worked out to be 3.6 meters. So here is the point charge, here is the surrounding sphere, it's which is a long distance, 3.6 meters. That's at 10 volts. If I go to the 20 volt equipotential, that should be located at 1.8, the 30 volt at 1.2, the 40 volt at 90 centimeters. So I'm plugging into these formulas, I'm putting these values in, and I'm finding out where those equipotential surfaces are going to be located. All right, that's probably a good place to wrap up for the day. So if you guys have questions, stop by office hours, and we will get back to you at the next lecture.